This portion of the chapter is going to be about the oxidation of aldehydes and ketones, and then we'll go on into the nucleophilic addition reactions that involve hydrogen and oxygen nucleophiles. And I want to point out that the order that I'm going to go through this material is different than the order that it's in the book, because I have it organized by the nucleophilic atoms. So the first thing is, why are aldehydes and ketones different in reactivity, even though they came out approximately the same place on the redox scale? And there are two reasons for that. One is the steric accessibility. Aldehydes have a hydrogen on one side of the carbonyl, and so it's less crowded than the ketone that has carbons on both sides of the carbonyl. The potential for more steric crowding is there. I do want to remind you that when we talk about nucleophiles approaching the carbonyl carbon, they're going to come from the top or from the bottom, but nevertheless, the potential interference in that approach by larger or bulkier groups can play a role in how easy that reaction is. And so the steric factor is obviously going to be less for aldehydes. And the other thing that's a factor is the charge separation. If we look at a carbonyl in this form, we have positive character, negative character, and in the extreme case, an honest to goodness positive charge on the carbon and the negative charge on the oxygen. And if you look at this from the standpoint of it being an aldehyde, that carbocation character is positive because an aldehyde has to be at the end of the chain. And for ketones, it would be a secondary carbocation character, and we know that primary carbocations are not quite as stable as secondary carbocations. And so from that standpoint, aldehydes are a little less stable in this format than ketones, and so that makes them somewhat more reactive. And if you have a reaction that involves a molecule that contains both functional groups, an aldehyde and a ketone, it is actually possible to do some of the reactions we're going to be looking at, selectively get all the aldehyde reacted before any of the ketone starts reacting. And if you have a way to monitor the progress of the reaction, you could do the reaction on the aldehyde and not have too much of the ketone having reacted before you get all of the aldehyde done. And where this comes in initially is in the oxidations of aldehydes. We know that aldehydes are a little more reactive. We just talked about that. And we've mentioned several times in the past that aldehydes are easy to oxidize. Remember where they are in the redox scheme. They're right in the middle of the redox carbon progression. And so they can be oxidized to carboxylic acids. And we saw evidence of that process back in chapter 8 when we talked about aldehydes coming from ketones. Coming from alkenes. We could oxidize alkenes, and if there were any vinyl hydrogens, alkene type hydrogens, then they would get further oxidized from aldehydes, go on all the way to carboxylic acids, and you couldn't stop, because permanganate also oxidizes aldehydes. And in chapter 17, we also talked about specialized reagents to enable us to stop when we oxidize primary alcohols. If we use one of these specialized reagents, PCC in the older books or the Desmartin periodinane in the 8th edition, we can stop the oxidation of an alcohol at an aldehyde, but other oxidation methods like chromic acid, for example, are going to take that aldehyde and keep going to the carboxylic acid level. And actually, aldehydes are able to be oxidized in air, in the oxygen in air. It's a little slower, but aldehydes are very common in a lot of our food products like cinnamon and vanilla and so forth. So the quality of the product degrades over time because of the oxidation in the air. So you need to keep those kinds of molecules sealed up away from air as much as you can. And your spices are going to be fresher when you first get them because of that oxygen in the air oxidizing the aldehydes. And we'll see a little bit more about oxidations in a later chapter, but for now, really what you need to know is the specialized way to stop at aldehydes. We're interested in making aldehydes in this chapter, and which is kind of a review of some things we've seen before. Um, and and then there's going to be one other when we talk about ketones. So there are a few ways to oxidize ketones. In this book, they only give this one, and they're fairly specialized because ketones are pretty easy to oxidize. Excuse me, pretty difficult to oxidize, um, and they're pretty robust for a lot of the things that affect aldehydes. But in one example of something that you can do is use permanganate in aqueous basic solution, which is written here as permanganate with water and sodium hydroxide. So it's a basic solution, and we don't really have the details in this chapter. We won't see the details on how this works or why this works until like chapter 22 or so. But I can tell you it has to do with that keto-enol equilibrium that we've talked about when we talked about alkyne hydration. They go through this vinyl alcohol or enol form, and that's actually what's getting oxidized here. And so they've picked a symmetrical ketone, so it doesn't matter whether you cleave this bond or this bond. There's only one molecule you're going to get out, and that's just chop open the ring and both ends turn into carboxylic acids. If you had an unsymmetrical ketone, then you get a mixture of products. And, you know, so it would work on open chain ketones. It's just that you would get mixtures of products. So all of the examples in the book for this reaction are going to be limited because of that mixture avoidance idea, that we're just going to see it useful on simple symmetrical cyclic ketones. And so this is just an example of that. And we won't see any other oxidations of ketones in this book. Okay, so let's talk about these nucleophilic addition reactions. As I said at the beginning of this section of material, I'm going to organize them by the nucleophilic atom, which we're abbreviating as Nu, with the pair of electrons. These are nucleophiles, which means that they love the nucleus. The nucleus is where the positive charge is. And so all of these nucleophiles are going to be Lewis bases. And they're going to have a pair of electrons to share. They may be anions, or they just may have some negative character, but at the very least they must have control over a pair of electrons to make a new bond to the carbonyl carbon. And the particular atoms that we're going to look at, I'm going to go in this order. We're going to look first at hydrogen nucleophiles, and they're going to be in the form of hydrides. And I didn't draw an unshared pair of electrons here, but this negative charge is the hydrogen with a pair of electrons. We're going to look at oxygen nucleophiles, and the kinds of things you could have are water or alcohols. And we'll also actually talk about hydroxide ion as an oxygen nucleophile. And you can have carbon nucleophiles. We'll talk about Grignard's, cyanide ions, and also Wittig reagents, which is a new kind of thing. We need to build up information about that. And then nitrogen nucleophiles, which nitrogen comes from amines. So, like I said, it's not in the same order as the book, but it's a progression that I think is very sensible, and I will use a similar progression when we get to chapter 21, emphasizing the nucleophilic atom. So here was our overview from the preview section of the book on carbonyl chemistry. So we need to evaluate our reagents and find the nucleophilic atom and decide, does it have enough of a negative charge, or it may have negative character, but if it's really a strongly nucleophilic atom, it can follow the red path. And so it will go to this tetrahedral intermediate, and then the oxygen wants to see if it can make a double bond back with the carbon. And usually here, these things are going to all stick, because Y is hydrogen or carbon in the case of aldehydes and ketones, and those are not good leaving groups. R group represents either a hydrogen or a chunk of carbon as well. And the nucleophile in these cases is going to be one of those four things we just said earlier: hydrogen, carbon, oxygen, or nitrogen. And so most of the time when it gets to this tetrahedral intermediate, the answer to the question of do you want to make a double bond is no, and so it just sits here until you protonate and get to your addition product. Now, if your nucleophile is not good enough to get started with just some positive character here, then we'll start out by protonation, and then you get a resonance stabilized species where the carbon has more of the time real positive charge, and then just adequate nucleophiles will then be able to react with that and get to your tetrahedral product. So that's basically the pattern we need to keep in mind for how we're going to go through these reactions. And the first one, as I said, we're going to do is hydrogen nucleophiles. We've talked about the reduction of aldehydes and ketones in chapter 17 when we were talking about making alcohols. And we could use sodium borohydride or lithium aluminum hydride as our source of hydride ions, and so that's a negative charge species, so it can follow the path for excellent nucleophiles and get to the tetrahedral intermediate. So right here, hydrogen is now in the place of this Nu, and so then we follow that with a source of protons and we get a tetrahedral product. And when we studied this in chapter 17, we were interested in alcohol products. You notice that because we're adding hydrogen as our nucleophile, we're not changing the degree of the carbon. So an aldehyde is a primary carbon, will make primary alcohols. If you have a ketone, then that's a secondary carbonyl carbon, and that will make secondary alcohols. So here are some examples. So here's a ketone. And as you see, that's a secondary carbon, and we make a secondary alcohol. If we have an aldehyde, that's a primary, we make a primary alcohol. In either one of these cases, we could use lithium aluminum hydride. It's a little more hazardous to deal with and maybe a little bit more expensive, and so usually we'll use sodium borohydride, but you need to keep in mind that you could use lithium aluminum hydride if you wanted to, because it's a stronger reducing agent than sodium borohydride. Alright, so let's talk about oxygen nucleophiles. And the most obvious oxygen nucleophile that you might come up with would be water. And the unshared pairs of electrons on oxygen in the water are not drawn in here, but you know that they're there. And so if you do this, this is actually a type of hydration reaction. And this is shown as an equilibrium. And the reason it's shown as an equilibrium is because this hydrate of aldehydes and ketones is not really very isolatable, and so we pretty much can't do this and stop here. But what they show you in the book is this is actually the reason why you can't stop at aldehydes in aqueous solutions of oxidizing agents, because this guy is the one that actually gets further oxidized to the carboxylic acid, and if it came from an aldehyde, it keeps going. But if this had been a ketone, we would just stop here, and this would be another R group, and then that wouldn't do this. Okay, so so the bottom line here is that technically oxygen in water can be a nucleophile on aldehydes and ketones to get to a tetrahedral, but we can't isolate it, and so it's not useful. So what else? Well, if you kind of take a step further along, you might think about an alcohol as kind of the first daughter of a water molecule. So you replace one of the hydrogens on water with a chunk of carbon. Now, the way I've written out this reaction, I have written this as an aldehyde, but it could be a ketone, in which case there'd be another R group here. And I've called this R prime just to distinguish it from this R group right here. So some random aldehyde or ketone with some alcohol, you put in acid catalysis. Now remember the pathway that we talked about. If it's just an okay nucleophile, then maybe we need to put in the acid first, and that would facilitate the ability of the thing to attract the so-so nucleophile And so if you do that, then you get to this product, which I'm going to call a hemiacetal. And that would be the end of the nucleophilic addition reaction. Okay, it's just you've added the elements of alcohol across this double bond. You put the hydrogen up here and the rest of the alcohol molecule down here, and you get to this hemiacetal. This is a very important biological pathway because sugar molecules, a lot of them are aldehydes, and some are also or ketones, and so most of them are alcohol aldehydes, but we do have a few ketones that are sugar molecules, and they cyclize internally by doing this hemiacetal formation. So this is an important biological pathway. Now the oxygen in the alcohol molecule we can actually go on and lose a water molecule, and I'm going to show you the mechanism for that in a minute. But the product that you get if we replace this OH with another alcohol molecule is called an acetal. So you have a hemiacetal or a full acetal, and we lose a water molecule. And you notice that all of these reactions are equilibria. And so the next, obvious question is, well, is it useful? Can we drive the equilibrium? How do we do that? And we can apply Le Chatelier's principle. So in Le Chatelier's principle, it says that systems that are at equilibrium try to maintain the equilibrium. And so one of the ways we can drive this is to remove one of the products as it forms. And so if we remove water as it's created, then that will pull this stuff along to create the full acetal. The other way we can fiddle with Le Chatelier's principle is we can use one of the starting materials in excess. And usually the way you do that is you use the alcohol as a solvent in addition to being a reactant. And so by having a large excess of the alcohol, that will push the equilibrium along. And so let's look at the mechanism first. So this is that top pathway where we have a sort of an okay nucleophile. So we're going to start out with acid catalysis. And that's going to protonate. We get the real positive charge on the carbon, and then we're going to use an alcohol. The alcohol oxygen is the nucleophile to get to this point. And so at that point, we will have the hemiacetal, and we will have finished the nucleophilic addition part. And so this really is catalysis. If you look at it stepwise, we protonate the carbonyl, we get to the protonated version, and they didn't draw in the resonance structure, but we just looked at that. This is what I wanted. We're at this resonance structure, so they didn't draw this picture, but it belongs right here with this one. Okay, so the carbon has more positive character. So now the unshared pair of electrons on one of these alcohol oxygen unshared pairs of electrons will react with that, and you'll get to this tetrahedral product. And now from the solvent, it could be alcohol molecules, or if you've already produced some water molecules, in case you're wondering where did that come from, it could be alcohol molecules. Pick up this proton. We lose that as a proton, give the pair of electrons back to the oxygen. Excuse me. And here's your tetrahedral product, the hemiacetal. You notice that we put a proton on, we take a proton off, so it truly is catalysis. You're not consuming your acid. Now, at that point, you've finished the nucleophilic acyl addition reaction. You have actually finished that at this point. If you have excess alcohol, more than 1-to-1 ratio, then it can, in the presence of this acid, protonate the oxygen. Now, let me go back to the previous slide again. If we take off this proton, okay, we get to here. We now put the proton back on and put it here. Now we get a different possible leaving group. All these steps, notice again, all these steps are equilibria, So if we had put the proton back onto the oxygen, the blue oxygen, we would just go back here. But if instead we put it on the red oxygen, then we've got the potential to lose a water molecule, and that's a different outcome than what we'd had if we would have just put it back on the blue one. And this guy is again able to leave because we can create a resonance stabilized species. So so this guy, now they've kind of turned it around, so don't let that bother you. We're creating a second bond between this oxygen and this carbon, and this guy comes off as a water molecule. So they've turned it, kind of moved this up here, all right? And so this guy is also resonance stabilized, so the carbon has positive character, full positive charge part of the time, which is going to attract another unshared pair of electrons from another alcohol molecule. And there's some water in here, but we're going to use enough alcohol that it's more likely to collide with an alcohol molecule. And remember, if we put a water molecule in here, we would just go back where we came from. So if instead, if it reacts with this as its nucleophilic atom, now we again get a protonated oxygen, 3 bonds, and now we can again give that proton away. So let's see, we put a proton on here, we lose the water molecule, but we also take the proton back off. We're still only talking about a catalytic amount of acid. Typically the acid that they use is like a drop of sulfuric acid in your solution of your alcohol and aldehyde or ketone. Just a drop of sulfuric acid will do it. And now you've got a product that's called an acetal. And so going on past the hemiacetal, we can keep going to this full acetal. One of the things that you might be curious about is, okay, so I said that the sugar molecule chemistry was important to get to hemiacetals. Going on to the full acetal also is important because the sugar molecules can do that with each other or with other things. And so this chemistry is really important for biological systems, even beyond sugar molecules themselves. And so I've put it all on one page here. So the book had it, you know, where I had to put it out on 2 slides. So I've got it all kind of crunched up here together. And so let's just go back through it again. So we protonate the carbonyl. We have the resonance stabilized species, which then attracts the unshared electrons. So we make a 3rd bond on this oxygen. It's got a plus charge. We lose the proton. We get to the hemiacetal. We've accomplished the nucleophilic addition reaction. But that can keep going. Okay, if it keeps going, then we could put the proton back on to the other oxygen and lose the water molecule, and through resonance, so I've drawn these guys out, the resonance stabilized species could react with another oxygen from another alcohol molecule and lose a proton, and you can get to the full acetal. Now, why I have these oxygens in red is I want to talk about how do we know that this is the right mechanism. You know, you've got to wonder, how do people know about all these little steps, you know? And people have studied that, and one way they've studied it is by using oxygen 18 labeled alcohol. And you'll notice if we follow where the red oxygens end up, all of the red oxygens end up in the products. Okay, the water molecule, if your original aldehyde or ketone is just straight plain oxygen 16, that all comes out in the water. And all the labeled oxygen is in either the hemiacetal, right here, the hemiacetal or the full acetal. The reason that's important is it's telling you that you never break the bond between this carbon and this oxygen. Okay, they always stay together. So the only carbon to oxygen bond that gets broken ultimately is the one between what was originally the carbonyl carbon and its oxygen. That's the bond that breaks right here when we lose this water molecule. Okay, so you're never going to break this bond between this carbon and this oxygen and this alcohol. And so that's one one of the ways we know this pathway. I mean, imagine another scenario. You might have reasonably asked the question, well, if we put acid in, why didn't we protonate this oxygen? And if you had protonated this oxygen, then you could have lost that as a water molecule, but you see that would involve breaking this carbon to oxygen bond, and we know from this isotope study that we never break that bond. Okay, so we know that we start out by protonating this, and so another reason that this is a favorable pathway is because we have this resonance stabilized protonated species here, and so that's a good place because it's resonance stabilized, and because we have this oxygen labeled study, we know that this is right because we never broke this bond. So another question you might have is, well, how do we drive the equilibrium if we want to see some examples of that? I told you one of the ways you can do it is you can put in excess alcohol. Now this particular alcohol is a dialcohol, so this is ethylene glycol, and that's the antifreeze stuff, and so excess means excess. And so if we put in this alcohol, one of these oxygens reacts, and then it closes up the loop and makes the full acetal, and so you make this kind of acetal, cyclic acetal. This is very common to use this as a protecting group for the ketone. In other words, we're going to disguise the properties of the ketone as this acetal, and if you look at it, an acetal is kind of a double whammy ether off the same carbon. And if you remember from chapter 18, ethers are fairly stable. They only react with strong acids. They don't react with bases. And because we've got this ketone tied up in this acetal, we could keep it from reacting with bases or nucleophiles as long as it's in this form. But it is subject to hydrolysis by aqueous acid. So if we put in water and a drop of acid, this guy will go back to here. Okay, so we could drive it by using excess of this, but we can go back again if we want to, and we need to sometimes. So these acetals are sometimes used as protecting groups, which just means disguise its property. And here's an example of some other alcohol, and so we can go to this through this reaction. And another way to drive the equilibrium is to do an azeotropic distillation. And you may have done one of these in lab with a slightly different setup, but basically you put your starting material, so all this stuff would go into the flask, and you heat it up, and when it boils up, the toluene makes an azeotrope with the water that's being formed, and so it's going to have a boiling point that's less than 110 degrees. When you have that azeotrope, an azeotrope is a constant boiling mixture of two things or sometimes three things. And the boiling point of that mixture is different than the boiling point of either of the components. And so when you boil this stuff at this lower boiling point, it comes up, and then when it cools off, toluene and water are not soluble in each other, so they separate. And so you'll get a little layer in here of water is going to be on the bottom because it's more dense than toluene, and you'll have toluene on the top. And so there's little graduated scale markings on here, and so you could quantitatively watch for how much water is going to be formed from this reaction. So if you had 1 mole of this and 2 moles of this, you would make 1 mole of water, which is 18 grams or 18 milliliters. So when you got to 18 milliliters of water in here, then you'd know you were done. When this thing is going, it's going to fill up with this mixture of toluene and water, and the toluene is going to be on top, so it's just going to flow back. And so you would recycle the extra toluene, and you just keep running until you get to the amount of water that you're expecting to get out, and then you can stop. This is called a Dean-Stark trap. And like I said, in lab you've done something like this, and the equipment's going to look slightly different, but in principle this is the way it works. So we drove the equilibrium by removing the water as it formed, and then we can make our acetal that way. And because we've got excess in here, we're going to go all the way to the acetal and not stop at the hemiacetal. One of the obvious questions you might ask is, well, okay, do people ever stop at the hemiacetal? And in a lab, usually they don't. They usually are doing this in a laboratory situation because they want to disguise or protect the ketones and the aldehydes character, and so they want to go all the way to the acetal. In the biological system, as I mentioned, sugar molecules cyclize. They go back and forth between an open chain form and a closed chain form, and there's alcohols on the sugar molecules and either aldehyde or ketone group elsewhere in the aldehyde or the ketone sugar molecule, and so they cyclize internally. They make a hemiacetal, and because that's a biological system, they can stop there in the biological environment. And so yeah, those things are frequently found as hemiacetals, but in a lab we usually just go all the way. Now, I'm going to talk about a reaction that kind of combines the idea of both an oxygen nucleophile and a hydrogen nucleophile in one, and it's called the Cannizzaro reaction. And it's actually an example of disproportionation, which is a term you may or may not have heard in general chemistry, but what it means is a molecule that can self-redox. So some of these molecules are going to end up being oxidized by the ones that are being reduced, and or vice versa, whichever way you want to think about it. And this is only going to work for aldehydes, and these aldehydes can have no alpha hydrogen. Earlier in the material, the earlier section of the material that I did on this chapter, we talked about position names in these molecules by Greek letters. So aldehydes only have one alpha position, and that carbon cannot have an alpha hydrogen on it, which means that there's several families of aldehydes that fall into this category, but it is limited to those kinds of aldehydes, and it's important biologically, and it's useful in lab as long as you've met these criteria. And we need to know about this because it's kind of a side reaction that can happen to us. When we get into chapter 23, then we'll come back and mention this again. So I'm going to explain what it is, and it's really easy to run for the proper kind of aldehyde. So it looks a little exotic, but it's really easy to do. And so what we do is we put in hydroxide ion as our oxygen nucleophile. So this counts as an oxygen nucleophile type reaction, and that might even be something that you wondered about. Well, we went from water as potential oxygen nucleophiles to alcohols. What about hydroxide ions? If you put a hydroxide ion into an aldehyde that has no alpha hydrogen, for example, an aromatic aldehyde, then it can do this Cannizzaro reaction. If you put a hydroxide ion into an aldehyde or a ketone that does have alpha hydrogens, something else is going to happen, and we'll study that in chapter 23 as well. So different things, because it's pretty basic, or too basic for other things to go on. This is what it's going to do. So here's your oxygen nucleophile. It's attracted to the positive character carbonyl. You get your tetrahedral intermediate. And this time, when the oxygen says to the carbon, hey carbon, do you want to make a double bond again? The carbon checks, and because of this particular situation, the hydrogen says, okay, I can leave because I can react with another one of these guys. And so we're going to actually balance this equation with two of these for every one of these. Okay? And so this now becomes a hydride nucleophile on another molecule of aldehyde. And so we had an oxygen nucleophile, we got to here, we got a hydride nucleophile coming from there to here. And so let's see what happens. The hydrogen that was already on the aldehyde and the new hydride is causing reduction of this aldehyde molecule, so that's going to take us down to this benzyl alcohol. And the when it goes to here, you know, you get your tetrahedral intermediate, and then the oxygen is just like this, except now you've got hydrogen, hydrogen, okay? And so now when the oxygen says, hey, carbon, you want to make a double bond, now those hydrogens don't want to leave, and so it sits there until you put in the aqueous acid to neutralize the solution, and you protonate it, and so you've made benzyl alcohol. So that carbonyl got reduced by the hydride pair of electrons. The other molecule, what happened to that? When it remakes this double bond between the carbon and the oxygen, it's still got this OH on it, and so that becomes a carboxylic acid. Now, at that moment, it is going to be in this basic solution, and so actually it would become an anion. But when we put in the aqueous acid, it gets protonated as well. And so we get that guy. So the carbonyl in some of the aldehydes gets oxidized. When this pair of electrons leaves, this carbon is changing redox levels. So those guys get oxidized, these guys get reduced, and they're kind of doing it to themselves. And it counts as an example of a hydride nucleophile as well as an oxygen nucleophile. And self-redox because the same molecule is ending up in both places. So, like I said, it's kind of a specialized situation. So this carbon right here has no hydrogen on it. So this is the family of any kind of other stuff on the ring, like other chunks of carbon, and there's a lot of things that could be on the ring. As long as they don't react with a hydroxide ion, you can have whatever on the ring. And so the family of aromatic aldehydes works. Formaldehyde itself, which is just the one carbon aldehyde, could work. And also if you have any kind of quaternary carbon directly attached to your aldehyde carbon, that would work. So here's an example, the one that we just saw. 2 molecules of benzaldehyde disproportionate to benzyl alcohol and benzoic acid. Here's an example of a quaternary carbon directly attached to the aldehyde carbon. So there's no hydrogen here, so that's the alpha position, no hydrogen. You put in your sodium hydroxide and then follow it later with aqueous acid. And so some of these guys end up reduced, the other half end up oxidized, and so you make your 2 molecules that way. And formaldehyde, I mentioned, is, you know, there's no alpha position at all, and so it works too, and you make a molecule of methanol and a molecule of formic acid, and there you go. So there could be whatever chains of carbon out here, as long as this carbon is quaternary. Of course, this is the only one in this family, because if you put anything else on there, then you're in a different family. But all kinds of things here, all kinds of things here. As long as this first carbon has no hydrogen, you can do this. And that is the end of this section of material where I'm discussing nucleophilic additions that involve hydrogen and oxygen nucleophiles.